mean, the goal of what I'm going to say now is that what we learned from Josef is that there is a correspondence between three manifolds, meaning the theory of three manifolds. This is only an analogy. And the theory of final manifolds. And so these numbers, no matter in the spectrum, no matter actually how big they seem to be, actually when computed lead to birational invariants. So Rene likes cubic, so I'll demonstrate what these invariants are for cubic. Actually, just one of them. I mean, so I only understand the meaning of the first number of the spectrum. Others, this is something for you to study, but already the first one gives results which are much stronger than what is known. So now, I mean, so this analogy, I'm not sure you can find it anywhere, but it's based on interpretation of recent papers of Mina Ganachik. So, last few papers, and each of them is like 200 pages. So I don't claim that I understand it, but because she interprets in her way papers that I've written, so I do understand at least part of the work, okay. And but you really need to, I think actually the last one is wrong, but that's besides the point. And so it's a physics interpretation of what we get down with the engineering. So, and the other papers, actually, it's probably the thesis of James Paskarev. And he is Bulgarian, but doesn't speak the word in Bulgarian. So, so he claims that he interprets a paper that I wrote with Orlov and Kapustin a long time ago. And that is true, but so I'll reinterpret his interpretation today. So that, so probably the closest to what's needed is his last paper with Nico Sibila, which we can try to, we can find on the internet, and it's from this year. I mean, also the Ganachik's papers are, just from May of this year. So now, so yesterday, so now basically build a correspondence and so tell you what corresponds to what. But yesterday, Alexander asked me if there is a differential equation involved, and indeed there is a differential equation involved in all the story. And so that's actually the starting point for our consideration. And so this is a Knyzhnik's logical equation. And so unfortunately, I mean, this is a differential equation is the hardest part of mathematics, and so I'm not going to interpret this today. So, that. But in any case, so I mean, I'm not going to use this today, but so the solutions of this equation are actually so-called conformal blocks. And so it was a very popular subject in physics. I'm sure that if you go to the Nuclear Institute and find anyone who is older than 65, they will know this very well. They might not know mirror symmetry, but this thing they will know very well. So unfortunately, Knizhnik, someone that I knew, died at the age of 27 in 1986. But so, of course, this was developed quite a bit after that. And what Ganachik actually notices that this equation, in the case when the source, sorry, the target is Q1 minus points, it's nothing else but what is called the quantum differential equation. And so this one exists in literature quite a bit, but it was written in this form for the first time, sorry, in the paper that I wrote with Max and Tony Pantev something like by now 13 years ago. And so the K is the operator of quantum multiplication on this funnel, let's say. G is certain grading operator. And F is the solution of this equation. So this is so unital generating function, and so of course their expansion gives you the Gromov-Witten invariance. So now in this particular case, this equation actually coincides. You can get after you do some transformations, of course. But so the asymptotics of their sub-exponential growth solutions actually can be compared. And so this is some theory of central manifolds, which Alexander knows very well. And so the spectrum can be seen that Josef was describing, can be seen in one more way, just as asymptotic of the solution of this equation. So that is the point that I wanted to add, is that you can indeed, in all these appearances of the spectrum, you can add one more. So asymptotics of the solutions of the differential equation. And then, so this point of view that in this particular case, these two things coincide, actually has quite a bit of interesting applications to uniformization. And so I hope we will discuss this later, but it was already noticed by mathematicians that actually this could be used. So, I mean, today I won't discuss this direction, but certainly there is another possible application to mathematics out of this. So now, let's start building our correspondence here. So remember that what we learned from Josef is that so that we have these three manifolds. So they can be obtained from S3s by surgeries on some nodes, right? And so two surgeries differ one from another by a complicated sequence of Kirby moves. But still, I mean, the corresponding invariants that were built here, they somehow do not depend on these moves. And so now, the important thing was this cabling procedure, which was briefly described yesterday of this nodes, but and you can actually compute out of this cabling the spectrum itself. So now, in case of symplectic manifolds, open symplectic manifolds, you have analog of this, and so this does appear indeed in this paper we wrote with Orlov and Kapustin a long time ago, but it was put in a better form by Kunzevich. In 2009, and the paper, of course, is never published, but it's called something like symplectic manifolds and homological algebra. You can find it on his homepage in IHS. So, but the idea is the following, that you can actually take an open symplectic manifold and associate with it a skeleton. And so the skeleton allows you to completely recover mirror symmetry. So that's the idea of Sims. And in particular, so in the same way as you are connecting to these nodes singularities, singular curves. So here you can actually, the skeleton with this open symplectic manifold, you can actually correspond to one of these good models. So, and now let me give for you one example. So that I'm not going to do the skeleton of Fano manifold, although there is a paper that I wrote with Linton Grana where this could be found. But so let me do something simpler. I'll describe what is a skeleton of a Riemann surface, and then give you the idea how to do the Landau-Ginzburg model of it and So now this idea that to a singularity you can write sorry, I apologize. To a node you can actually write algebraic interpretation using so-called matrix optimization. It's not the idea that was introduced by a physicist. In fact, was introduced by an Annotation a long time ago. So this guy is certainly very much alive. I think he's director of MSRI. But so the idea belongs to Eisenberg. And in fact, so obviously neither I nor him knew where is this all going at that time, so there was no mirror symmetry, but definitely I've heard him talk about this in Bulgaria in 1986. So, but there was no mirror symmetry at that time for sure. So, yeah, this thing existed. So, now, this is what we are going to try to do. So we are going to imitate this procedure of Heisenberg. It's not only Heisenberg, it's first to start with the topologist procedure and then to algebraize it. So we'll do this in the case of Fano manifolds. But as I said, Fano is too complicated, so let's do Riemann surface. And so what you do is you do a split up the Riemann surface to pair of bands. And then you kind of, instead of working with a pair of bands, so correspond to this I'm terrible, this a link, I mean, to be precise, a skeleton, and so that is going to look like so you operate on this dumbbell graph, and then so you start, so you have several of them, and then so you put here other parts of the Riemann surface for which you further do the same procedure and you actually correspond to this skeleton. So this could be found in this big, in the thesis of Pascal that I had mentioned, or this paper with Sibilla that with Sibilla which I mentioned. So now, so this is the analog of this cable graph that Josef was talking about. And now the idea is that, so that goes back to Kunzerich, is that this data actually allows you to build a Landau-Ginzburg model. And so, in other words, in the same way as Eisenberg corresponds to this some singularities, you can do some singularities here as well. And so I'll just give you what the procedure is. So it can be, I mean, for curves it was spelled out in this paper that wrote it for law, but in general it's in James' thesis. So the idea is that to H, sorry, okay, the vertex here in this then you correspond the following matrix factorization. And then to an edge, so we have GM equals C2, and then YZ, and then to bigger simplices, you correspond similar things in such a way, and then we have functors. These categories of matrix factorization. So this is how you put these things together. At the end of the day, and so it's the same way as Eisenberg does this putting of matrix factorization together, and so there is a cabling procedure which they call splicing, explained very well in a book actually by what's the name of it? But which one? So actually they are all family. So I knew Mike Norman and Bernard Norman, but this one of them is the grandfather and the other is the uncle of Walter Norman. And then it doesn't. So now I mean, there's a book written a long time ago how one does this. I mean, how do you go from cabling to this matrix factorization and splicing? And so it's absolutely there's an absolute parallel procedure that you have to do here. So let's write it here, cabling to splicing, and then so here we have skeleton to model this book more. So, I mean, basically, what classically we have is the classical theory of singularity. And so, what that was explaining yesterday. So you have here singularity and you have a modeling operator. And then what we have is that so what is it? E in power I spectrum is equal to the eigenvalues tau. And so similarly, you have very non-classical theory of one of these book models, and in this case, again, there is a monotomy. And again, we can define a spectrum in such a way. So now, the spectrum has a lot of nice properties. And so, I mean, I will not bother you today with all these properties, but for the argument I'll need 1, and that is very important when indeed you can actually obtain it classically from, so this is work with zip and everything. So you can obtain this semi-continuity out of the topology. So what does this mean is that well, okay, so people like here PDE, so you introduce additional parameters here. And upper semi-continuity on this language, remember that the spectrum, these are the asymptotics of the sub-exponential closed solutions of this equation. And basically, upper semi-continuity just means that the solution for t equal to 0 are bigger, meaning the asymptotics. That the solution are bigger of the asymptotics for the solutions of t not equal to 0. Namely, the special value, you get the biggest asymptotics. So, it's a little bit easier to prove these things combinatorially than to do it for PD, although if someone actually gets it from the PD, there will be tons of other applications. I mean, I don't know how to do it. Sasha can do it, but I mean, there should be some restriction coming from the non-commutative cost structures on this PD, and then one should be able to solve this in some natural way, but I don't know how to do this, so I prefer to do combinatorics this way. So now, there are many other nice properties that Spectra usually satisfy, like it was already mentioned, so-called Tom-Sebastiani. And you know, they can behave in an arbitrary way, and so if you want to get invariance of rationality, this actually can be used. So I'll put a lot of nice properties. And this can be used for, I mean, namely if you want to invoke all the numbers of the spectrum, but today I'll just deal with the biggest one. So I won't bother with other properties, but so there is something which is called Hartree inequalities. Very restrictive. So these things really, I mean, whole structure really puts restriction on how these things can behave, and eventually, if you want to do non-rationality, this could be used.
Sorry, but this you mean this about the variance of the spectrum?
Yeah. But I mean, meaning that, so if it, so they're all, I mean, they have certain kind of Bernoulli distribution properties. So the difference between the smallest and biggest divided by 12 is bigger than, well, all right, so 12 times k. No, but in this case, actually, it is true.
In the quasi-homogeneous case.
Yes. And yeah, okay, so now there's mean, a lot of things which are hidden here. So in particular, there were some notes that Josef was talking about, and these are notes with trivial Seifert spheres. So now, sorry, what am I talking? Seifert forms. And so this actually does appear in this correspondence in an essential way. So this can be seen here under deformations, but we deform Rolando-Ginzburg model in a certain way that the corresponding function is not holomorphic, but very close to holomorphic, and so as we call it in a paper, linear tone asymptotically holomorphic. So these functions have the nice property that the whole Lefschetz theory package work for them. Therefore, you can define an monogamy, which is going to be with nice properties and integral, and therefore the spectrum makes sense in this case as well. But so the categorical phenomena of this type of nodes is something which is called phantoms. So they do appear in category theory. These are categories which have trivial Gaussian homology and not even trivial K theories, but they're not trivial. So they are, no matter if the spectrum doesn't see them, they also are a strong obstacle to rationality. But so this we'll discuss later. So in any case, so this is only part of the correspondence between these Fano manifolds and then the three-dimensional manifold, so it's an analogy. And so now what I would like to do is to just demonstrate in one simple application of this analogy, no matter that it's simple, and it still allows you to do results which have not been known before. But I'll start with a very simple example, which we all know very well, and everything is known about it. And so I'll demonstrate how this package works on this example. So the example is a three-dimensional cube. Smooth three-dimensional cube. So it's cubic in P4. So I mean, this is one of the most notorious varieties in algebraic geometry. And so it's been studied for quite some time, and its non-rationality was proven first by Clements and Griffiths, who computed the intermediate Jacobian of this variety, and has shown that intermediate Jacobian was shown that so this is a Billian variety, but it has a theta divisor, but this theta divisor has too small singularities of the co-dimension. Singularities in this case is equal to 5. And according to the theory of Biot-Meyer, which it's a very tricky thing, and so this singularities, if this happened to be a Jacobian of a Riemann surface, it it's a close 4. So this cannot be a Jacobian, so the cubic is not obtained by point of T3, so that's the way the argument of Griffiths and Carries. Sorry, I apologize, Carries and Griffiths went 50 years ago. But, so we will look at this from a little bit different perspective. So, there is a Landau-Ginzburg model that you can associate with the procedure that I described. So this function, so this function x plus y plus z to the third over x, y, z equal to w. So this is giving you a family of
It's plus a z?
Yeah. It's giving you a family of KT surfaces, open KT surfaces. Of course, you can compactify. And so this Landau-Ginzburg model looks like that. So the argument that I'll be giving you now, it ideologically uses mirror symmetry, but actually it doesn't. So I'm just kind of giving you what's going on, but everything that I need can be computed without mirror symmetry, as you're going to see. I mean, of course, you have used it in order to introduce all these invariants, but at the end of the day, you really only use this ideologically. Everything can be done with, without any mirror symmetry. All you need to do is to think about your manifold X as it was thought about 50 years ago, algebraically. But also you think about this as a symplectic manifold. So you put A and B side of the mirror symmetry of the very same manifold. So you think of it as a manifold which is algebraic, but also a manifold which is symplectic, to which you can apply this procedure which I have just explained. So for this you don't need any mirror symmetry, but so now if I have a symplectic manifold, I can define for it so-called quantum equation. So first I have the operator of quantum multiplication by k. In this case, eigenvalues. So lambda 0, lambda 1, lambda 2 in this particular case. And so a theorem tells you that the homology of X actually splits as a direct sum of 3 pieces. I mean, in this particular case that we are studying, and in general, and I'll explain what are these 3 pieces in this case that we are studying here. So, this is a Hodge diamond of the 3-dimensional cubic, and so lambda 0 corresponds to this. So this piece of the Hodge structure gets separated, then lambda 2 and lambda 3, so lambda 1 and lambda 2 correspond to these pieces. So now, the theorem actually says that this splitting is a birational invariant. So, which actually means that modulo pieces that I can add by blowing up things of coordination 2 and half, so this splitting remains untouched. So, if I start doing some birational transformation, I can only add pieces here which correspond to submanifolds of coordination 2 and half, by listing this part of the splitting is preserved. I mean, the way to think about this in terms of mirror symmetry is that whatever I started blowing up, so I'm just adding here additional singular fibers. But these actually are untouched, so they're not interacting with each other. So now, what I'm going to do is do the following thing. So I remember that I have this equation, and this equation actually is defined to a non-commutative post structure. So I'm going to reduce it only to this piece, to H0. So lambda, H lambda 0. For this again, I don't need any symmetry. So I take this equation star. So I reduce star to H lambda 0. So now what I'm going to do is to compute the spectrum, or if you like, asymptotics of this equation, when restricted to lambda 0. And I'll just give you a formula which works in general. This is for the biggest number of the spectrum. And it's like that. For hypersurface, for complete intersection, it's similar. It's 2. And so here, we have, let's say, a Fano hypersurface of degree d in P n. So, n minus 1. So in the case that we were considering, d is equal to 3 and n is equal to 5. So I have a cubic in P4. So if I'm not mistaken, if you compute this number, you get that delta is equal to 5/3 in this particular case. So let's see, I have 3 minus 2, 5 minus 3, 2 times 2/3, 4/3. 9/3 minus 4/3 is 5/3. So now, all right, so what's the big deal about this number? So, of course, once again, this is the highest number of the spectrum. There are others, but I'm not going to need them today. Eventually, you will. So, So the thing to notice is that if I have any x and I blow it in y, and so I do the same trick, so I have here whatever I have for the splitting, but then I'll have this y, the core structure of y, adding to the thing, and I restrict my equation of nature y, then this spectrum of this differential equation, when restricted to y, has the biggest part, just dimension of y. So now, that's a little bit tricky because, in fact, I can only compute this for t equal to 0. But then, upper semi-continuity tells me that if I move away from 0, this can only go down. So if I move in the whole modular space, or if like in the whole Frobenius manifold, which is classical thing is singularities, the spectrum of this type can only go down. So that's really an important observation, and let me just, by making it, explain how to prove non-rationality of the three-dimensional cubic. So now, if I have x to be obtained by blowing up P3 in a curve, or many curves, so the maximum number I can get here is, as the spectrum is, dimension of this curve. So the maximum number I can get here is 1, and if I go to away from t equal to 0, this number can get only smaller. From another point, the spectrum that I have for the cubic, for this piece, is equal to 5/3. And so, no matter how I move in the modular space, so this 5/3 can never come closer to 1, it's bigger than 1. And therefore, there is no way that I can obtain the cubic, the three-dimensional cubic, by just blowing up P3 in curves, so that implies that smooth three-dimensional cubic is not rational. So, of course, I have chosen here a number that, sorry, I apologize, a funnel that you understand very well, and a funnel which, classically is known very well, quite well, but I mean, obviously, I can do this in other cases in a very similar way. So let's see what is so let me just point out that we are not talking very general here, which was our methods give you. We're talking every, because these numbers are not for very general, they are for every. And in fact, it doesn't matter what the field is, the Gromov-Witten theory works over any field. So these arguments work over any field as well. So now there are experts on stacks here, like Enrique, and it doesn't matter if this is a smooth variety or stack. Gromov-Witten theory works on stacks, so we can apply this for rationality of stacks. If you are master of this, how this thing called, twisted sectors or something like that. So if you can actually deal with the twisted sectors and get them out of your way to compute this species in the homology, so you can work in singular cases and so on and so on. Let me just point out to you that smooth Del-Petro surfaces, these are the smooth funnels of dimension 2, are 9. Singular ones, so with group actions, funnels of dimension 2, if I'm not mistaken, are over 40,000. For very few of them, actually, we have a criteria for rationality, and for some of them, of course, this method gives you non-rationality in the very same way. So you just need to look at this, and this is surfaces. So the three-dimensional funnels which are singular, so I think that they are in the billions, and so you can certainly apply this method there as well. So now let's try something that is not so exotic. So let's say that quartic in P, what is not known, quartic in P5. So I have 4 here, then 2, P5, 6 minus 4. So what do we get? So we see the number is 3 that we get for the quartic in P, the quartic in P5. So if the number is 3, then so what I want to show is that the quartic is not obtained by blowing up P4 in some surface. So the number that I'll be getting here is 2, and since 3 can never come down to 2, I mean, so then you get in such a way a different proof that the quartic, any smooth quartic in P5 is not rational in such a way, ever, not very general, ever. Now, let me demonstrate some weaknesses as well. Well, you can still do a lot, but let's say the 4-dimensional cubic. Sorry for that. So, okay, it's 4 again, but I have 2 times, or is it 5? Minus, no, 6. So I get 2. So now delta is equal to 2 for the 4-dimensional cubic. And we are in trouble here because both numbers are, so if I blow something which is in co-dimension 2 and delta is 2. This argument doesn't quite work for the 4-dimensional cubic. But this is just because I'm just oversimplifying it too much. I mean, just doing this numerology. I mean, all these things are much richer. There is gamma lattice and so on. And this could be used as well. And so you will be getting that 4-dimensional cubic is actually generic. 4-dimensional cubic is not rational, but using a little bit more, some analogs of the cipher form, which I have put under the cover doing this kind of things. But just numerology doesn't do this. So now, I think that we can get quite a bit out of the other numbers, but this is something for you to do. I mean, so far, I have just made use of the only and the biggest number in this spectrum. So there are already in Josef talk, you notice that there are many other numbers. And so now notice that they have a lot of restrictions, and so Tom Sebastiani, Hartling, and many other restrictions which can be employed by in order to do. You just need contradictions, and so that I think will give you many other applications. And of course, once you learn how to compute that, make sure of all this work. So as I said, there are other classical applications of this analogy, to uniformizations and so on, but we'll discuss this a little bit later. So when it comes to literature, so I mentioned these papers of Ganachik and James and Paskalev, but hopefully we'll be able to finish some introduction to the subject very soon, and some of these things will be spelled out in certain form. Now, I mean, for people who want to explore application to uniformization, I certainly will try to do that. The important thing is these two equations actually in the very simple case of curves minus point happen to be the same. So that's not use. All right, so I need to go change my passport now, so which has expired, and I'll see you tomorrow. I mean, I'll be back later, but I don't know how it's going.
Thank you.